Hello guys, welcome back to my channel Memo African Motives. Still working on engineering science and form. So actually in this platform we shall be focusing on stress, strain and Young's modulus. So that's actually a continuation from the last part that we worked on. So this one is from February 2022. We just want to see how ask this question and how we're supposed to answer this type of a question that we are given. So guys, if you're new to this channel, you can consider subscribing so that you become part of the family, Memo African Motives. Okay, so without wasting much of your time guys, let us quickly rush through the question and take the information that we are given. So always when you are answering questions, make sure that you list down the information that you are given. So in this case, we are given that on 7.1, a tensile force of 120 kilonewton is applied to a bronze rod. Take note, this is a bronze rod, causing a stress of, we are given the stress. The original length of the rod is 4.5 meters and the Young's modulus of bronze is 96 gigapascal. So these are pascals. So this is giga, this is 28 megapascals. All right, so let's just leave the information guys. We are given a tensile force, so this is actually 7.1. so we are given a force of 120 kilonewtons. So just write your information guys as it is 120 kilo, even though you know that it's 120,000. Just like write like this, and you must know that kilo, this is times 10 to the power of what, of 3. If it is mega, that is times 10 to the power of 6. If it is giga, that is times 10 to the power of 9. All right, so that is what you're supposed to know there. Now we are given that it causing a stress of, so we are given the stress in this case. Remember your stress, the formula for the symbol for stress is this one. That's your stress, which is equal to 28 megapascals. So this is 28 megapascals. Just list your information, okay? Then the original length of the rod is 4.5 meters. We are given the original length. So this is just a length here. You can write it as L0 or you can just write it as L like that. Just leave it, which is 4.5 meters. Then we are given the Young's modulus for bronze is 96 giga. So this is the Young's, which is given by E like this. All right. That's the Young's modulus or for elasticity of the bronze. So this part we are working with bronze. All right. So this is 96 gigapascals. So just list down information. All right. So now the first question is calculate the following: the diameter of the rod. So which diameter? Where are we having the diameter, guys? Okay. So this is a rod. So which means actually we are referring to a cylindrical rod, something like a cylindrical rod. So definitely we know that for us to have this, because we are going to have a circle here, so this is the area that is going to be created from this circle here. All right, so where are we going to obtain this area from? So what you do is that you're in exam guys, you want to find diameter, so you have to find where you can obtain the diameter. So the diameter can be obtained from area. Why? Because we know that this is the formula. So let's see how we are going to get this diameter guys. This is 7. We know that area is given by pi d squared over 4. So that's your area here. But we do not have this area. If we can have this area, which means we can just make our d to be the subject here, because you can just cross multiply, which is going to be like over 1. So if you cross multiply, it's going to be 4a is equal to pi d squared. You divide by pi, which means your d is going to be 4a over pi. Since it is d squared, so it's going to be the square root. If you make the subject, because you're going to divide by pi, then you remove the square by putting the square root. Okay, but we do not have this value of area. So what you're going to do is to calculate the area first from the information that you're given. So from your formulas there in your formula sheet, you're going to see that here we have got the stress, which is equal to the force over area. So which means we can make area here because we have got the stress here. We also have the force, which is this one. So which means we can simply make area the subject. Okay, so this is 7.7. So we all said that stress is equal to force over area, and this is the area that we want here. So we're going to make area to be the subject because we got this and we also got this. So just cross multiply here is going to be like this, which is equal to F divide by the stress because we want area. So therefore our area is force over stress. Okay, so let's substitute, guys. What is our force? This is your force, which is 120 kilo, and you said kilo times 10 to the power 3. So it's going to be 120 times 10 to the power of 3. Everything over the given stress. Now what is the stress here? It's 28 mega, and you said mega is times 10 to the power 6. So it's 28 times 10 to the power of 6. All right, so there, guys, make sure that you have to use your calculator properly, guys. This is what you're going to obtain as a decimal. Is going to be 4,286, yeah, something like that, times 10 to the power minus 3. Okay, so area is measured in square meters. Remember that, guys, that area is measured in square meters. So now you have the area, so you can determine the diameter that you remember want to calculate the diameter, and the only thing that was missing was the area. So the area is there, therefore our diameter is going to be, this is what we are going to have now, the square root of 4 times the area, which is this value here, 4,286, all right, times 10 to the power minus 3. Okay, guys, this is minus 3 here, everything over pi, like this. So take note, this is minus 3. We have got minus 3 here on the exponent. So using your calculator, you're going to obtain this endless decimal, guys. This 0.373 87221865. This is what you're supposed to. So make sure that you use your calculator properly here. This is what you're going to obtain. So that's your diameter, guys, which means since this area was in square meters, this diameter will be in meters. So it's going to be 0, just round off maybe to 3 significant figures. We can just have 0, 7, 3. This 7 can change 8 into 9, and this is in meters. So therefore that is going to be our diameter there. So as you can see, guys, it's very easy. If you are working with stress strain there, what you're supposed to know is to connect the formula. So as you can see, we just connected the dots between the area, between the stress, which had got the force and the area, and we obtained the area from this formula here, then the diameter from the area, because we know that area is pi d squared over 4. So we can make d to be the subject, we can calculate our diameter just like that. So that was the first question. Let's see another question on 7.12, which is the strain. All right, so now you need to find the strain. So strain is easier. Also here, let me show you what we have in this case. If you are to cross check here, we have got many parts that we have where we can obtain strain. We can obtain strain from this formula, here, because we've got stress and strain from the Young's modulus here. We can obtain our strain. Also, we can obtain if we got the change in length, but in this case we are going to see if we have the change in length, but we can obtain our strain from this formula of Young's modulus. So how is this going to be possible? That's the question now. How is this going to be possible? All right, so from the formula there, I want you to see this one. It's the one that I'm going to take. This one, the Young's modulus. Okay, so 7.12. So the Young's modulus is equivalent to the stress over the strain, just like that. So we are going to just make what we need here, the formula, because the information is there here. We've got the information, the Young's modulus is there, the stress is there. So which means strain is going to be stress over Young's modulus, like this, because you're going to cross multiply. It's going to be like this. If you cross multiply, it's going to be like this, where this is your strain and this is the Young's modulus is equal to the stress. So you divide here, as you can see, so that you're going to be left with the strain, which is stress over the Young's modulus. So as you can see, that is the case, guys. So this one is a matter of substituting into the formula the stress. You've got the stress here, which is, remember, this is mega, which is times 10 to the power 6. So you've got 28 times 10 to the power 6 over the Young's modulus, which is to the power 9. So this is 96 times 10 to the power of 9. All right. So what are we going to obtain now? That is the question. All right. So from this part, guys, this is the decimal. Actually, it's not a decimal, but it's a decimal. 2,9166. So it's going to be like that, guys. But there's going to be a 10 to the power minus 4, which is at the end there. All right. So take note about that. So you can just round off, this, which is going to be a 7 here. 2,917 times 10 to the power minus 4. And this is just like a constant. It's not like it's a constant actually. So there's nothing, because here, remember, you had pascals over pascals, so there's nothing, there's no unit there. So this is what you're going to obtain just as a constant value. So take note, guys, about this. You just formulated, you made what you want, which is the strain to be the subject from the formula, as I showed you from the formula sheet, that you can actually take this information from the formula sheet. It can help you a lot. All right, so what you need is to just list down your information. Then on another question, which was on 7.2, still on this part, to make 15 marks. You see, guys, a lot of marks, these ones. All right, we are given that the compressive stress on a steel pillar with a rectangular profile of 200 millimeters by 300 millimeters and height 6 meters is 200 gigapascals. Calculate the working load on the pillar. Okay, so let's just try to list the information again. So this is a rectangular pillar that we are given here, something like this. We've got a rectangular pillar here. So guys, remember that on a rectangular pillar, this is length and width. You just have length and width. So we're going to divide 6 millimeters, because this is millimeters to meters. So you divide by 1000. So it's going to be 6 divided by 1000, which is 0.06. So you're going to have 0.006, okay, which is now in meters. Then you do the same here. This is guys, we are converting. What is wrong here? We want to convert on this part here, not on this part. Okay, so guys, we are on this part, not 0.06. We are on this part here, guys, on this part. So this is going to be 0.22. I was now converting on the other part now. So we have got 0.22 meters, and another one is going to be 0.3. This one is going to be 0.3 meters. All right, so that's what you're going to have. Now we are given this is a rectangular profile, and the height now, which is from this portion to another, because it's going to be connected to another, because it's a rectangular object that you're given here. That's where we are going to be remaining now with a height here in between of what? of 6 meters. That is the one that we are given here. So to give us a volume, so we have got a height of 6 meters, which is the length. Actually, just leave it like that. Then we are given that this compressive stress that which means we are actually given the stress in this case. So we are given the stress, which is 200 gigapascal. Remember, giga, we said it's going to be times 10 to the power of 9. Okay, then what else are we given here? Calculate the working load on the force. So the working load, this one is actually the force. We are talking about what? About the force in this case. Okay, so where are we going to obtain this working load, which is the force? Where are we going to obtain this value? All right, so it's also a matter of connecting the dots also. So I want you to see from this formula that we talked about previously, where we are given stress. Stress is force over area. All right, so we've got stress, which is equal to force over area. That's what we have. And what we need in this case is the working load, which is the force. So I can actually make force to be the subject 1 times cross multiply. So force is equal to the stress times the area. All right, so which means we need the area first. So where are we going to obtain this area from? That is the question now. So if you are to cross check, we are given 0.3 here and we are given 0.22. So which means we can actually obtain our area because it's a rectangular part that we're talking about, that we have here. Even though it's gonna connect to somewhere, but here we've got a rectangle which is gonna give us an area because we've got the length and the breadth. All right, so our area in this case is going to be length times breadth, which is 0.3 times 0.22. So now we can have our area. I calculated this and obtained 0.066. So this is what you're going to have in square meters, like that. So from this area, guys, we can just substitute here because our force is the one that we need. So it's the stress, which is this one. So I think this 6 is not even working. So it's 200 giga. So remember, I said giga is times 10 to the power of what? 9 times the area, which is our area 0.066, like that. So multiplying this, what you're just going to do, guys, to avoid confusion here, because this is 10 to the power 9, is going to give us a big value. So just imagine, just leave it like that. Okay, multiply these two numbers, 200 times 0.066. So if you multiply these two numbers, you're going to obtain 13.2. all right, so this is going to be 13.2. But remember that you ignored 10 to the power 9, so you're going to multiply by 10 to the power 9 because this is a bigger value. There is no need for you to actually change. This is force, guys. Force is measured in what? In newtons. So this is force, which is measured in newtons, like that. So take note here that this is a bigger value. Just like you are working with 10 to the power 6, you multiply maybe 2 times something like this. Just ignore this. Okay, multiply these two numbers, 2 and 4, you obtain 10, 8 times 10 to the power 6, like that. Easier. So it can be much easier than to include this 10 to the power 9. So you just ignore it like that. So this is the working load. So the working load, you're talking about what? About the force here. So that's the working load. All right, so that's what we had, guys, from this part here, because they actually ask these typical questions like this, where you need to connect also the dots, like I said, of the formulas there that you'll be given in your formula sheet also. Then 7.3, we are given a steel bar. We are given another condition again. It measures 6 millimeters by 12 millimeters and 1.8 long, just like what we were given here. So take note, guys, it's the same situation, just like what we're given here. So this is going to be like this. So it's a rectangular steel bar again. So we have to convert again to meters, just like what we did. So 6 divide by 1000 is going to give us 0.06, 0.006, like this. This is now in meters. That's 1, 2, 3. Yes. Then this one, 12 is going to be 0.02, 0.012. It's now in meters. So we've got the length and the breadth there. Then we've got the height, like I was saying. When you connect this to another rectangular, because there's going to be another rectangular object there. So when you connect, that's where we have got a height which is 1.8 meters long to connect it to the what? To the other path. So it's just like the length between the two. So there's no need for us to worry. Okay, so we're just having a length there. So which is 1.8. That is the length that they will be talking about. All right, which is in meters. It is compressed by a force. So take note, which means there is a compression which is taking place there. So that's our force. So we've got our force. As you can see, guys, it's a matter of taking down information, substituting your information in the formulas. You're done. And here's a deformation, which means a change in length, because when it is being compressed, there's going to be that shift in length. So that is the change in length that you're given. So the change in length, you can write it as x, or you can write it as change in length like this, or you can write this as x, because on your formula sheet, x represent the change in length. So this is going to be 0.037 in millimeters. So this is something like okay, let's just write in millimeters first. 0.37 millimeters. Okay, that's millimeters there, or it can be 0.00037 meters. Okay, if you want to use meters there. So the other thing, guys, is that we can have, this was 6 millimeters. Remember, this was 6 millimeters. Let me just write. You never know what's going to happen. Maybe you might need to use this in millimeters. So let's just write in millimeters and also in meters. Okay. Then the first question is calculate the stress. So we just need to know the formula for stress. But as we saw that from all these formulas, we're working with stress, and we say that stress is equivalent to force over area. So this is 7.31, where we said stress is the force over the equivalent area. So we got the force here. So what we need is the area. So definitely the area is going to be obtained from this rectangular block that we are given. It's a rectangular block. So we've got length times the breadth, which is just like length times width. Okay. So you can just substitute here because area is equals to length times breadth. So we are given the force 32 kilo. Remember I said kilo times 10 to the power of 3. All right, so it's going to be 32 times 10 to the power of 3 over the area. Is a rectangular shape, so we said it's length times breadth. That's our area. So the length is 0.012 by the breadth. This is your breadth here, which is 0.06, like this. Okay, so that's force over area, so which means you're going to have our stress here. Okay, so what are you going to have? This is the value, guys, that you're going to obtain. I don't know how many these fours are, but it's 4, 4. It's 1, 2, 3, 4, 5, 6, 7. There's 7. 1, 2, 3, something like that. 2, 4, 6, 8, 9. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, like this, guys. That's what you're going to obtain, comma 4. So that is so you can actually convert this. I think it's gonna be, because we said remember, guys, you just see if it is possible to leave it 10 to the power 6. We said it represents what? That's mega. 10 to the power 9, that's a giga. So in this case, how many digits do we have before the comma? We have got 3 here, 6. So 9 is, if you use 9, is going to be 0.444 gigapascal like this. But if you use 6, if you divide by 6, you're going to be left with 4 like this, which is in mega pascals. So here, these are just like normal pascals. So to convert to mega, you simply divide by 10 to the power 6. The one that you want to multiply to, you divide by it. So you divide this number by 10 to the power 6 or 1 million. It will be in mega pascals. That is the idea there. Okay, so that's what you simply heard from this part. Then the stress, the strain. So strain, where can we obtain our strain from this information, guys? So also it's a matter of playing around with the information that we had, and this is where I listed the information. All right, remember, this is where we have, so we need to find the stress. So from our formula sheet there, we have got this formula for stress, which is for strain, not stress, but this one is for strain, which is the change in length. So take note, like I said, is the change in length, which can be written in terms of x, like this, over the original length. So this can be in terms of x, or you can just write it like this, change in length over the original length, just like that. So where do we have the original? And so the change in length here, we talked about it here. This is your change in length, which we said it's actually in meters. This is in meters, 0, this millimeters. Always just know that millimeters is 10 to the power minus 3. Okay, so millimeters is 10 to the power minus 3, or you can use this decimal here. All right, so which means our strain is going to be the change in length, which is since our original length was this one, which is 1,8, is in meters, you can use this in meters, which is going to be 0,00037 over the original length. And this is our original length, which is 1,8. So you divide by 1,8. So that's what you're going to have, guys. So if we divide these two numbers properly, we are going to obtain this endless decimal, 2,05555 and again times 10 to the power minus 4. All right, so what am I going to do? I can just round off this to 3, which is 5. This is going to change into 6 times 10 to the power minus 4. So we've got the strain from the change in length over the original length. And remember, from the previous part that we also did on strain, we obtained that this strain is actually a constant value, because you're actually dividing. Here is now meters and meters, so they will cancel. It just remains like as a constant like that. So that's how they ask these questions, guys, and we need to at least work on more question papers as we prepare ourselves for the exams which are ahead of time. So that's it, guys, from Memo African Motives, working on engineering science and for question papers and revisions to prepare ourselves for the exams here ahead of time. So if you are new, guys, you can consider subscribing so that you become part of the family, Memo African Motives. Till we meet again.